Hi everyone. In this video, we're going to talk about some theorems, postulates, and definitions related to segments that are some of the basics that we need to know for geometry. Now, you have already learned these properties of equality. When you have a property of equality, we specifically mean that it has an equal sign. So some of these properties can also be properties of congruence. A congruent symbol looks kind of like an equal sign, but has a little has a third line that's a squiggle on top. Now, properties of equality only can exist when there is an equal sign between the two things that are happening. Properties of congruence only exist when there is a congruent symbol. There's also a lot more theorems or properties and definitions that have equal signs and congruent signs, but when you're trying to decide for something that's the same term, such as reflexive, if it's equality or congruence, you want to look at what is the symbol that's being used. I want to remind you that the word congruent is when they are the same size and the same shape. So while equality talks about numbers and values and lengths and areas, congruence talks about the shapes. So you might have two triangles that have the same shape, so they are congruent. Their areas are the same, so their areas are equal because area is represented by a number. So the entire shape is what we would say is congruent, but the numbers are equal. So the numbers are equal, the shapes are congruent. So the first thing that we're going to learn is that there are some properties of equality that also are properties of congruence. So for our first one is our reflexive property. And our reflexive property is the one that tells us that for a segment AB, it is congruent to itself. So any shape that you have is definitely congruent to itself. It's the same as itself. So that is our reflexive property. You notice I know it is a property of congruence because I have a congruence symbol in the middle. Our symmetric property of equality let us flip things around, right? This was our flipping. So the same thing here. If you have a segment that is congruent to another segment, then you could flip that congruence statement. So you're able to flip congruence statements just like you can flip equality statements. And our last one was our transitive property. So this one was kind of our chain of statements. Our chain was what let us say that if we have segment AB is congruent to segment CD, and segment CD is congruent to segment EF, well, we now have a chain because we have here AB congruent to CD congruent to EF, if I put it all together. So I can just take out that part in the middle, right? Just skip over that part in the middle and we get AB is congruent to EF. So these three properties of congruence were very similar to the properties of equality. We just say it is a property of congruence because now we're talking about shapes and we're using congruence symbols. So now we are talking about some definitions. So definitions are our parts that will let us take words that we have or symbols and change them. So our first one is our definition of congruence, which kind of tells us what congruence means. Segments are congruent if and only if they have the same measure. Those of you might notice that this if and only if is a biconditional. So that we're going to have two conditional statements. One where we say that if the segments are congruent, so if segment AB is congruent to segment CD, then the lengths are equal. And also, if the lengths are equal, then I can say that the segments are congruent. I want you to remember that this is the length of segment AB, right? If you have AB without the line on top, it's the number, right? This represents a number, which is why I can use an equal sign. So the definition of congruence is great because it lets us go back and forth between knowing things are congruent and knowing numbers are equal. This is how we're able to turn congruent statements into equations. Because you in algebra learned how to solve equations, but if I just tell you the shapes are the same, you need a fact that's going to connect those two. We also have the definition of a midpoint, which tells us that if you have a midpoint, so if M is the midpoint of segment AB, then we know that segment AM is congruent to segment AB, or MB, sorry. That would be segment MB. So if I have segment AB, so segment AB, then this would be point M in the middle. So a midpoint, it's a point that cuts a segment in half. It's the point in the middle. So the definition of a midpoint tells us that if you know a point is the midpoint, then you know the two segments are congruent. Now this statement is not a biconditional, so I can't flip it around. Why do you think that is? Well, if I had segment AM, so say this is segment AM, then I could also make this segment MB, and it doesn't matter that they are the same length. I know the drawing isn't great, but if they were the same length, that's still not the midpoint because I didn't have an original line in the first place. So this is a counterexample for why you can't take the converse, remember converse means to flip, of this statement. Because there could be situations where you have two segments that are congruent, but that you don't actually have a midpoint. Our last postulate that you have already learned is our segment addition postulate. So if I have segment with A, B, and C, so A, B, and C are collinear points, and B is between A and C, then I know that AB plus BC equals AC. Remember, because I don't have the line symbol on top, I know that those are the lengths of AB plus BC. That's why I can use an equal sign because I'm talking about numbers here. So those are some postulates and definitions related to segments. Thank you for watching.